Hi everyone, good morning. I'm Akshay Prasad. I'm from RV College of Engineering in India. I'm currently pursuing my BTech in computer science. So first of all, it's a great pleasure for me to be presenting to such an esteemed crowd. Let's start. Well, in my summer, I actually used machine learning techniques to detect fraud in credit card transactions under the mentorship of Roger Dave. And finally, I moved on to human activity recognition after finishing this a bit earlier than expected to explore certain data sets and certain machine learning algorithms. So before we actually move on to the details, just a quick poll. How many of you actually feel safe making credit card transactions, or even for that matter, owning a credit card? Right. While you answer, I'll just move on to the next slide. So I'm pretty sure all of you know what credit card fraud is. So just a quick recap. Credit card fraud basically refers to any illegal means of obtaining, account information and then perform some unauthorized or illegal transactions on your behalf. So this is something that's very close to identity theft. And see, credit card frauds these days are very attractive and desirable, but they're often susceptible to fraud. So it leads to a lot of privacy and data breaches. So it's actually it's the challenge for a company to detect these fraudulent transactions in a timely and effective manner. So machine learning fits in perfectly to this because one, it's an expert in detecting anomalies and it's quick. So that's the reason we have used machine learning algorithms here. Now, while I was researching about this topic, I actually came across a few tidbits that I found were really interesting. Now, the Federal Trade Commission of the United States actually studied over 12 billion transactions and found that over 10 million of it was fraud. So essentially 1 in 1,000 transactions are fraudulent. 5% of the US citizens have been victims of credit fraud. And all this havoc is actually caused by a mere 0.04% of the monthly active accounts. So it's just a small fraction of people, causing such huge financial losses. And this came as quite a shocker to me. Your credit card details, your sensitive information is actually sold on certain card buying websites for a median amount of $27 per card. Some of the websites are Escator or there are plenty of others which have this option. Now, I'm pretty sure all of you know what techniques fraudsters use to get such illegal information, but just to give you a brief overview, they use skimmers, which are basically devices that read and store the credit card information when you make a transaction. It actually reads your data on the magnetic chip in the back of your credit cards. There's also phishing, which is where criminals pretend to be bank officials and then convince you to shell out certain information to them. You also have duplicate websites which actually try to pass off as authentic bank websites, and so you'll naturally be inclined to give out your passwords and PIN numbers to them. So now, my objective during this internship was given a series of transactions to identify and classify it as fraudulent or not. So the machine learning models I personally have used are random forests, which are more popularly known as learning trees in the HPCC systems. I've used a one-dimensional convolutional neural network and a long short-term memory. Now, coming to the data set, this data set is available on Kaggle. It's basically transactions carried out by European cardholders over a certain period. Now, this particular data set is essentially one big time series. So you can, I guess it will be clear if you look at the plot at the bottom of the slide. So it's actually a plot of the amount versus time elapsed. So you can sense that it's just one big time series, and it's our duty or our problem to get it into a fixed format to be used for a machine learning algorithm. Now, diving deeper into the data set, we can see that the time field, these are the first 5 records in the data set. The time field basically indicates the number of seconds that have elapsed since the first transaction has taken place. The amount field obviously represents the amount. Now, these V1 to V28 fields, they're actually the 28 most significant vectors after performing a principal component analysis on it. Now, for those of you who don't know what PCA is, I'll be giving you a brief introduction in an upcoming slide, so please bear with me. Then we also have the class field, which is basically a Y vector. The 0 represents a non-fraudulent or a legitimate transaction, whereas the 1 indicates that it's fraudulent. Right, now the models that have been used, I'll just try to give you a brief overview of it, some intuition or some sense of what's happening. Now, random forests, or more popularly known as learning trees in the HPCC system, they're basically an ensemble of decision trees. Now, decision trees are tree-like structures where the internal node tests a subset of the input features, and based on that, it tries to send it down to a suitable child node. And the leaf node actually is the ultimate classification of it. Just for your reference, I've added a simple decision tree at the bottom of the slide. So this decision tree basically decides whether a person should play golf or not. So you can see that the root node over here, it actually tests the weather. Now if it's cloudy, it sends it straight to the yes leaf node, so it's classified as a yes. If it's sunny, it's sent down to the left child node where that checks the humidity and so on. So that's how decision trees work. Now the objective in a decision tree is to train the, the internal nodes to make sure that it tests the right input feature and then sends it down the right path to ultimately to the right classification. Now in random forests, what happens is we have, just for this example, let's take there are 10 decision trees. So now each decision tree is actually trained on a random subset of input features. Now we wouldn't want to give each tree all the input features because then we'd end up with 10 identical decision trees, which is not desired. So we get certain, we take certain subsets, train each decision tree. Now if we have to, in a task of classification, what we do is we get the classification of each decision tree, put it to a vote, and the class with the highest number of votes is the ultimate classification. Now coming to regression, you'd probably consider taking some kind of average of all the outputs and get a final output. So this is how random forests work. Now coming to one-dimensional CNNs, this is a beautiful algorithm and I would have loved to go into the depth of it, but due to certain time constraints, I wouldn't be able to. But to give you a difference, an intuition about how one-dimensional CNNs differ from the two-dimensional ones. See, in a two-dimensional CNN, your input would essentially be one 2D image or any two-dimensional sample. So you would have a small kernel that would actually iterate through the image as shown in the figure to your right. So it would essentially be like looking at a dark image with a flashlight. Coming to the one-dimensional CNN, you would have a the kernel would cover the entire feature set of a time step, but it would cover multiple time sets at a time. So that's the essential difference. There are certain tweaks here and there, but this is essentially how one-dimensional CNNs work. Right, so one-dimensional CNNs actually thrive or specialize in certain places where the temporal locality is not of the greatest significance. In the sense, there's a lot of memory is not required. So this would particularly be seen in natural language processing or some short signals that you have. Right. Moving on to LSTMs. Now, long short-term memories are actually a variant of recurrent neural networks. The disadvantage of recurrent neural networks is, you see, when you have a recurrent neural network, you have a very high risk of exploding gradients or vanishing gradients happening. Case of such cases. So that's why LSTMs were invented to cut this down and to help have a greater memory in each node, and to make sure that that the gradients are it doesn't explode or it doesn't vanish. Now the input to the LSTM is the current time steps features and the previous output. So each node actually has a memory cell and 4 neural networks to train the memory set to determine how much memory to retain, how much memory to adapt to the new time steps features, etc. Now, I would have loved to explain the architecture, but again, because of time constraints, I wouldn't be able to. So please feel free to ask me these questions in the Q&A if you're further interested. I would love to explain these models. Right now, this is something that I tried out during my internship, which was really interesting. Roger Dave actually has a new bundle coming out, generalized neural networks. Now, this basically provides an ACL interface to Keras over TensorFlow. So it actually provides all parallelized TensorFlow or Keras operations in an HPCC systems cluster. Now, basically how this would go about is models are created on each HPCC system node, whereas the training, evaluation, predictions are all done in a distributed fashion across all nodes, and would finally come back to the master node for updation. Now, GNN is actually, for those of you who know the sequential model, Keras' sequential module, you would be pretty familiar with this. It can handle any neural network model. It could be a classical neural network model, a dense layer, to even as something as complicated as a long short-term memory network. In fact, you can also use a combination of networks over the sequential model. So that's a great addition to HPCC. It's still in its alpha version though, so it would be available to everyone. It will be available for everyone to use very shortly. Right, now coming to the pre-processing that has been done on the dataset. Now, see, principal component analysis in its essence is a dimensionality reduction technique. So the objective of principal component analysis would be, given a certain dataset with some amount of dimensions, to represent the exact same dataset with smaller number of dimensions without much loss of information. So I guess this figure gives you a very good intuition. You can see the plot on the left, it actually represents certain data points in a three-dimensional space. But if you see, all the data points are actually, aligned on that particular plane, which is represented by PC1 and PC2 axis. So if we could somehow project the entire space or entire data point set onto that particular plane represented by PC1 and PC2, we would essentially be presenting projecting the entire data set in a two-dimensional space, and you wouldn't be losing much information in the process. Now, PCA is an excellent technique to use when you have hundreds of dimensions with a lot of covariance between each of the dimension. The mathematics behind this would be the use of eigenvalues and eigenvectors, but again, I wouldn't want to go into so much depth. Another major step in pre-processing is the reconstruction of the dataset. So see, our ultimate aim is to classify a small series of transactions given, right? So this one big time series that I said the time series was having, 284,807 time steps. That has to be broken down into smaller. It has to be broken down into smaller time steps or smaller samples. So what I have done here is I've broken down this time series into n number of samples having 4 time steps each. Now each time step has 29 features each. Now these 29 features are the ones that I explained, where it has the amount and the principal components, etc. So in the case of learning trees, this two-dimensional input has to be flattened out because the learning trees don't support two-dimensional inputs. Now oversampling. This is something very critical, a very critical step in the training of the model. Now, if you go back into the data set, as I said, it has 284,000 and odd examples or samples. But in this, just 492 of these transactions are fraudulent. So that's the level of skew that we're dealing with here. It's a highly imbalanced data set. So we need to tread very carefully. We need to, even when pre-processing or training the model, or even for that matter, when we are evaluating the model, we have to keep in mind that there are an ocean of zeros and very few ones. So oversampling is one such technique to overcome such cases. Now, see, if you blindly give the same data set to the model to fit it, it would obviously be biased towards predicting a zero because it has only seen instances of zeros majority of the times. And that would not be the best performance, not the desired one at least. So what we do is one of the techniques used is we just blindly repeat the fraudulent transactions. So if we, in the data set, if we come across any particular fraudulent sample, we just append it to the database again. Now doing this, again, the downside would be that the model would tend to overfit the fraudulent cases. That is, it would tend to by heart the fraudulent cases. Again, this is not desirable. So what I have done is I've added a random 10% noise each time I append the fraudulent transaction. So in this way, it sees more cases of fraudulent transactions. In the meantime, it's not the same over and over again, so there's no risk of any sort of by hearting that can take place. Right. So this is just to give you a summary of the pre-processing. You can see that after the principal component analysis has been done, there's reconstruction of the data set. Finally, there's again this. What I've done is there's also a blind appendation to the data set. There are the fraudulent cases are repeated some number of times, and later 10% addition has been done to again ensure that there's no overfitting. Now the system architecture is similar to any model that you'd have come across. There's pre-processing, you split the data set, you train the model on the training data, you get the prediction and evaluation for the test data. Finally, there's some hyper-tuning that you can do to get that 1 or 2% increase in accuracy with the same model. So there's nothing unique about this. I follow the same procedure. Right, now the evaluation metrics. See, accuracy is not at all a good metric in this case. Usually people prefer to go to accuracy, but let's just assume that this model is, it predicts every transaction to be, non-fraudulent. Now, only 0.4% of the data set is actually fraudulent, or there are fraudulent cases. So if you give the data set or the test data set to the model, and it predicts that each of it is non-fraudulent, you would still be getting a 99.6% accuracy, which to any person or any machine learning specialist would be an amazing accuracy. But in actuality, the model is not performing well. In fact, it's a disastrous model. So accuracy is very misleading in this case. So what I've decided to use are the three metrics that I'm using are precision, recall, and F1 score. Precision is basically true positives by the predicted positives. That is, I'm asking the model out of the positives that have been predicted, that is out of all the transactions that have been predicted as fraudulent, how many of it is actually fraudulent. Recall is basically the number of true positives in the total number of positives in the data set. That is, I'm asking how many transactions have been classified as fraudulent in the total number of transactions that are present in the data set. So F1 score is basically the harmonic mean of precision and recall. So we ultimately use the F1 score to judge the model to get a good trade-off between the two. Right. So coming to the results, we can see that LSTMs surprisingly perform, although it does give very good results. It actually gives an F1 score of 96.40%, which is great for any model. It does perform the least among the three, least well. So CNNs give amazing results. It actually gives a 99.39% F1 score, which is by far exceeding any of the models. But learning trees, CNN is a fairly complicated algorithm and pretty time consuming, whereas learning trees are much more simpler. But you can see that learning trees actually takes over the CNN by just 0.5, 0.6%, but still it does give a recall of 1. That is to say that all the fraudulent transactions have been successfully predicted as fraudulent. There are some false positive cases, but it does give an amazing result. Just to tell you that all of these are test accuracies or test scores. It's not on the entire data set or not only on the training set. So yes, we did get very good results. Now, just to give you some intuition about why this is happening. Before that, I just want to iterate through the power of HPCC. Now, the time taken without using HPCC, when I augmented the same code in Python, It actually took over 1.5 hours, but with HPCC, I was done within half an hour. And another thing, the results as well, I did find that there was a slight improvement in results when I used the algorithms, available within the HPCC systems. So yeah, HPCC systems have just been great. Right. Just to give you some intuition about why random forests or learning trees are performing outstandingly, whereas LSTMs are failing. Now the LSTM basically thrives when there's a long time series, where there's a lot of memory that's required and the temporal location is of great significance. Whereas, like I said, CNNs, they do not give a lot of importance to the temporal location. So in this particular data set, from this results, maybe we could infer that the temporal location of each transaction is not of the greatest significance. So the use of CNN is, giving us the 3 or 4% extra accuracy that we want. But the surprising thing is learning trees is actually performing marginally better than even a one-dimensional CNN. So the reason for this is pretty simple. Now learning trees, one, they do not overfit the data at all. It has the least tendency to overfit the data because as you can see, we have actually taken a subset of the input features. So there's very little scope for any overfitting to take place. And another thing is, each tree covers for each other's mistake. Now, again, we could go back to the wisdom of crowds, where, the entire crowd wouldn't make a mistake, but rather each person would cover for each other's mistake. So if, say, we had 100 trees, for this particular model to give a wrong classification, more than 50 trees should be, giving a wrong result. But usually it's not a lot of error takes place. So the rest of the trees cover for the trees which give the wrong values. So this is probably why learning trees perform way better than even an LSTM or a CNN. So right, this is my conclusion. Now a quick poll. Now do you actually feel safer with such algorithms, guarding your money in the sense? While you give your answers, I just have another thing to cover, which is the human activity recognition. Now I'd completed this part of my internship much earlier, so we wanted to get one data set and test it out where there's a lot of temporal significance. That is, it's a proper time series with a lot of significance given to each time step. So we actually opted to use human activity recognition data set. Now, human activity recognition is basically the problem of predicting what a person is actually doing based on a trace of their movements using some sensors. So my task was, given a sequence of accelerometer data recorded by some smartphone or any specialized harness for that matter, into some well-defined movements. Now here I've again used learning trees, LSTMs, and one-dimensional. I've used a one-dimensional CNN followed by an LSTM, which was the first time I've been using this. So it was very interesting. Right, so the data set is actually collected by 30 subjects wearing some waist-mounted sensors. In this case, it's their smartphones. So each of them is performing one of the 6 standard activities that is shown on your screen: walking upstairs, downstairs, sitting, standing, and laying. And also the video of each subject was recorded to manually classify it at a later stage. Now the data set now the data set essentially consists of the XYZ axis of the accelerometer data. Now this could be the linear acceleration as well as the angular velocity, that is the gyroscopic data. Just for your information, this was recorded at a right. So certain pre-processing techniques that have been used. Just to iterate, these pre-processing techniques are not done by me. This was readily available. The pre-processed data set was available to me. But just to give you an intuition, one, there were certain noise filters that were used to pre-process the accelerometer and the gyroscopic data. Again, there was a reconstruction of data set that was required. So we essentially broke it down to 2.56 seconds with 128 data points each, and there was a 50% overlap. Also, the accelerometer data was split into gravitational and body motion components, Gravitational is your downward acceleration, whereas body motion is your linear or your horizontal acceleration. So essentially, what I ended up with was a three-dimensional data set. So it had to be distributed across files. What we had at the end, we had 128 time steps in each sample, and each time step had 9 features each. So just to reiterate, the 9 features were the XYZ axis of gravitational and body accelerations, as well as the gyroscopic data. Now this has to be uploaded onto the landing zone. So I did write a program to flatten all this data set and upload it onto the landing zone of ECL. So I've gone through the other models, but this one-dimensional CNN followed by LSTM was pretty interesting. The CNN LSTM architecture actually involves using a one-dimensional CNN for feature extraction on the input data, and this data is actually combined by LSTM. It analyzes these extracted features as a time series and gives a prediction. So the CNN layer, what it does is it will read subsequences of the main sequence as blocks. So it extracts feature from each block, and it then allows the LSTM to interpret these features for each block. That is, it treats all the blocks as one essential time series. So there's these 128 time steps in this particular case has been broken down into 4 blocks of 32 time steps each. So right. So just to give you the results, learning trees were actually not very suitable for this case, but I included it just to show you the contrast. So it actually has a power accuracy of 84.356%, whereas the LSTMs, which again specialize with longer time series, gives an excellent accuracy of 93.034. Now note that this is a multi-classification with 6 output nodes, so getting an accuracy of 93.94 is it's a very good performance by the model. Now the one-dimensional CNN followed by LSTM gives us that slight 2% edge because of the features extracted by the CNN. So finally we did end up getting an accuracy of 94.717 with the help of HPCC. So, right, this is my presentation. This is the work I've done. I just want to iterate that I've cherished each and every moment working for HPCC, and I would love to continue to use it on any other project that I do from now on. So thank you so much. I'd like to thank my mentor Roger Dave again, Lorraine Chapman ma'am, and Trish Mikhail ma'am. Thank you so much. Thank you all.
All right, thank you. This has been a wonderful presentation. So Akshar, while you go and review the questions that have come in from the audience and prioritize them, I'm going to review the votes from the audience for your first poll question. And so that first poll question was, do you feel safe making credit card transactions? So 58% of you said yes, and 41% said no. And since we've had plenty of time since the last poll went through, let's look at that one. So that question was, do you feel safer with such algorithms guarding your money? And 76% say yes, and I totally agree with that. There's a lot of very good information in here. All right, so we're going to go ahead and take a quick peek at the questions that have come in. Are you ready, Akshar?
Yes, ma'am.
All right, perfect. So the first question is, what was your experience of using HPCC systems?
Yeah, thanks for that question. Yes, initially when I got into HPC, when I explored HPCC systems, it was pretty daunting. I had to learn a new language. I had to learn how distributed systems work. But as I actually started working on it, I used to appreciate it every day because of the computations that take place, the amount of complexity that goes behind the scenes. I used to appreciate it every day, and again, like I said, the results that I got, the speed that HPCC provided, it was amazing. So I had an excellent experience working with HPCC systems.
Fantastic. We're really happy to hear that. All right. Here's another question. What made you use random forests? Was there a particular reason that you chose that?
Yes, yeah, very good question. Yeah, I did, when I actually explored the data set, there was, I had the fear that there was going to be a lot of overfitting because there were a lot of samples and a lot of features. So there was a high risk of overfitting. So random forests, they're one of the least likely models to be, for any kind of overfitting to take place. So I actually wanted to try learning trees at random forests, and but to be honest, I didn't expect it to give such great results. I didn't expect it to overperform even a one-dimensional CNN, and it was a pleasant surprise for me to get that result.
Okay, perfect. All right, here's another question for you. Can you tell us the exact parameters used in the three models?
Oh, yes, definitely. Yeah, thank you for that question. Now, in learning trees, I used 32 decision trees with a maximum depth of, again, 32. I did a lot of permutation and combinations, and I got the best results with this particular hyperparameters. Coming to the one-dimensional CNN, in the first layer was a one-dimensional CNN, obviously, with 64 filters. 20, the kernel size was 20, yeah, it was 20 with an activation of ReLU. There was a dropout layer I used to avoid overfitting. It was followed by a one-dimensional max pooling layer. I think I used a pool size of, I guess, 2. And then there was a flattening layer, and finally a dense layer with a sigmoid activation to sum it all up and give us a binary classification. LSTMs, see, the thing about LSTMs is, it's not recommended to use multiple layers of LSTM, but because it may be giving you a 0.5 or a 1% increase in accuracy, but in the process there will be a lot of computational, it would be computationally expensive, but because I was working on HPCC, I had that freedom to actually add that second layer of LSTM and get better results. So I essentially used 2 layers of LSTMs with, I guess, 32 nodes and 16 nodes each.
Okay, thank you. Here's another question for you. I see your data is highly imbalanced. What technique have you used to deal with the imbalanced data?
Yes, yeah, it is highly unbalanced. I was dealing with a lot of skew. So the first thing, like I mentioned in my presentation, I used oversampling. But see, even if I oversample it, I can even if I append it blindly, say 10 times, I would still not get a good balance between the two. I would have to, balance it multiple times. So I actually opted for a small variant of data augmentation where I randomly added noise to it and made sure that it wasn't repeated, but it was still seeing certain instances of fraudulent cases multiple times, so that the bias towards 0 would, we would avoid the bias that the model would essentially take. Also, in the accuracy evaluation metrics, I had to use different parameters, different metrics, like I said, precision recall and F1 scores.
All right. Okay. So we have one last question here, and it's, well, actually we have several, but I can only do one more. The question is, can you please explain the use of memory cells in LSTM?
Oh, yes, with pleasure. I was actually hoping someone would ask this question. If I have enough, can I take another couple minutes to explain this?
Yeah, absolutely.
Sure. Then I just like to go back a couple of slides to get the architecture of LSTM. Right. So if you can see this architecture, there are 4 neural networks and 1 memory cell. Now the input to this particular is the current features, the current time steps features, and the previous output. So now the neural network to your right, which has a bias 0, as you can see, that is called the forget valve. Now what this particular network does is it trains these, it trains itself to output how much of the data, how much of the old memory should influence the new memory. So you can see that it has a sigmoid activation function, so you would essentially have an output ranging from 0 to 1. So this particular output is multiplied with the old memory and added to the new memory. So say for example the model says thinks it's apt to remember say 20% of the old memory. This particular model would give an output of 0.2, which is multiplied with the old memory and then added to the new memory. So the old memory is actually there's a network to using a tan-H activation function. The second the network with bias 2, you can see it actually is the old memory that has been input. So there's a tan-H activation function which actually has to go into the cell. You also have a third neural network which trains itself to give us the fraction of the new memory that has to be influencing the memory cell essentially. So you would multiply that with the new memory, multiply the forget valve's output with the old memory, add all of it, and that would be the input to your memory cell. So that's how memory is maintained. This is similar to a human brain, where we actually decide how much of your old memory to retain, and as new memory comes in, we tend to forget the old one while retaining part of it. So that's the intuition behind memory, the memory cell. Now again, the output is again a variant of the memory maintained in the memory cell. So use a tan-H function and a fourth neural network to determine what fraction of this tan-H activation function to be given as the output of this particular architecture. So I guess this would be the general intuition about the architecture of LSTM.
All right, thank you very much. That's a wonderful answer, very thorough. Thank you so much for this presentation. This has been very good.